The first big category is the intra-AS routing. Okay, so this is the routing protocol runs on the routers within NAS. It's also known as the interior gateway protocols, IGP. And here, interior gateway, not to be mistaken with the gateway routers. So gateway routers are the routers sitting at the border of an AS, having connectivity to other ASs. So gateway router there are to interconnect ASs. But interior gateways are completely internal. Okay? And then running on these internal routers within NAS, we have three very well-known protocols. RIP here, not really standing for resting in peace, it's actually Routing Information Protocol. Okay? But if it adds the impression, RIP, this protocol is also the oldest implementation of an intra-AS routing. It came with the Berkeley's BSD distribution in the 1980s, late 80s. And it's based on this principle, distance vector routing. Yeah, nowadays I'm not quite sure. I don't know if any network admins is running RIP for their intra-AS. But this other one, Ospf, short for Open, Shortest Path First Routing Protocol. This one, on the other hand, is very popular. Okay, so Open here stands for open source. Okay, RIP is also open source as it came with the BSD. So it runs also the shortest path first routing. Yeah, you guessed. Yeah, it's the Dijkstra shortest path algorithm that's running, and therefore it's based on the link state routing principle. And to make sure that we credit the right people, Ospf is actually based on ISIS. It's another routing protocol that was designed maybe 3 decades ago, by early researchers for distributed system research as well as these multiprocessor system research. So in those paradigms, having multiprocessors, if you want to pass the messages around, and these processors are actually forming an interconnected network, you also need to find a path to go from one processor to another processor. Okay, so at the time, those researchers, those computer scientists, have designed ISIS for the purpose. Ospf for internet, which is also a distributed system. It's just that it's very loosely connected distributed system. Yeah, borrow much of the design principles from ISIS. Third one is called the Idrip, Igrp, Interior Gateway Routing Protocol. Now, this one is completely closed. It's Cisco proprietary. It came with these Cisco routers, but it only is maintained until 2016, and obsolete afterwards. The reason for that is because Cisco is also beginning to embrace the idea of doing software-defined networking. So if you recall, in software-defined networking, routing is all done in the remote controller on the powerful machines. So the routers there, in SDN, pretty much are doing what? Generalized forwarding, and allowing the flow table being installed, and that's pretty much all. There's no need of running routing algorithms on individual routers. So starting from 2016, Cisco stopped maintaining Idrip because there's really no need, very little need of doing routings inside router. Let's speak about the most popular intra-AS routing protocol a little bit more, the Ospf. This we know, open here stands for the protocol being open source. Now, SPF stands for the protocol is based on the link state algorithm. So we see link state reports being passed around, over all routers inside the AS. In the end, each router is going to be able to regenerate the global network topology. And with that, we can then call the Dijkstra algorithm and compute the shortest path. So that's pretty much Ospf and how it works. It's based on the ISIS routing protocol, which we mentioned. Okay, it was designed several decades ago from these earlier researchers of distributed systems. Ospf simply borrow the design principle from ISIS. Now, the only thing that's new that we have not yet mentioned is this. Okay. We know routers are going to flood the Ospf link state reports, aka link state advertisements, to all other routers in the entire AS. Okay. What's not quite yet known is just this. These link state reports will be packaged into these Ospf messages. They are native IP packets, meaning the link state advertisements, we only append the IP packet header. And that's all. There's no TCP UDP packet header. There's no application layer packet header. Okay. Oh, and this link state, inside the link state report, what we have is just what? Okay, who's the neighbor and what is the link cost on the link connecting to the neighbor. Yeah, let's speak a bit more about the most popular routing protocol here in the intra-AS category, the Ospf. Open here stands for, the protocol is open source. Second, the SPF stands for the routing protocol is based on the link state principle. So we do distribute the link state reports all over the network. Therefore, each router will be able to reconstruct the global network topology. From there, then we call the Dijkstra algorithm to compute the shortest path. Be a bit careful though, these routers sending these link state reports, they'll be sending these reports in Ospf message. These Ospf messages are native IP packets, meaning the message itself, and then we append the IP packet header, and that's all. There's no TCP, UDP, or application layer header on top of that. Inside these link state advertisements, it's going to contain, who the neighbors are for this router. Also, the cost of the link leading to connecting to these neighboring routers. Again, ISIS routing, this is the predecessor of Ospf, designed by the early distributed system researchers. Now, what we haven't mentioned much yet are these. So these are the advanced features of Ospf. First of all, these Ospf messages, very important link state reports, they can be sent through a secure channel such that the receiver of these link state reports can authenticate the sources of the sender, therefore preventing malicious attacks. So if people can just send these link state reports around with no security check, one can easily inject a false route into the system. Second feature is this. One can actually exploit multiple same cost paths. So in case we come up with the topology such that the Dijkstra give us same cost paths and there are multiple of them, we could actually send data over these multiple same cost paths, which is nice sometimes. For each link, the metric for the link cost can be defined also differently for different type of services. For example, if we are trying to serve best effort traffic, meaning traffic does not require timely delivery, so the receiver can wait longer, then the cost of a satellite link, which the delay is longer, can be set lower, right? Because you would then prefer using the satellite link if the data does not require timely delivery. On the other hand, if the data is real time, then set the satellite link costs high. Therefore, we avoid choosing satellite link along the path to deliver the real-time data. And it allows also, Ospf allows also integration of the unicast and multicast. Now, if you recall in Dijkstra algorithm, in the end of the algorithm, what we ended up generating is from the source, from the router doing the computation, a shortest path tree. That is also saying that from that source, we could also send a copy of the packet along that tree to all the receiver in the network. So that is also a what? A very efficient flooding tree. Okay, that is a efficient multicast tree. So what multicast meant here is to send from one source to multiple receivers. Okay, so that the extra shortest path tree is also a multicast tree. So from that shortest path tree, we could do unicast, sending from one source to one destination. One can, of course, exploit that to send from one source to multiple destinations. And in the meantime, guaranteeing that it's also the shortest multicast tree. Okay, so multicast OSPF, MOSPF, is a very nice and easy extension of OSPF. Oh, by the way, one can also configure OSPF to run in hierarchy, okay, such as this one here I'm illustrating. So you see, there are two levels of hierarchy here. At the lower level, area 1, area 2, and area 3, okay. Inside each area, we could be running an OSPF, and all these internal routers within an area runs the same OSPF. It requires the same metric, link cost. And then at the higher level, you see, okay, in the backbone of this local area network, in the backbone of this AS, we could have also multiple routers configured. So these are called the backbone routers in general. Okay, some of these backbone routers might be at the border, okay, of the AS. They are also the boundary routers. Some of these backbone routers, okay, are also, okay, the manager of the areas. Okay, so this guy here and here and here are the area border routers. Okay, so the area border routers, boundary routers, as well as the other backbone routers together form the backbone, and they will together run also OSPF, but that is independent of the OSPF running inside each of these areas. So this slide is pretty much repeating what I was just saying. In the example, we do have two levels of hierarchy. Okay, so at the lower level, we have these local areas, and at the higher level, the backbone. Inside each local area, the link state advertisements will only travel within the area. Okay, the link advertisements for the backbone network will be traveling only within the backbone. And each node, okay, in each area is going to know the entire area's topology. And the node inside an area will only know the direction, okay, to the border area routers in case the destination is outside, okay, of the area. So these area border routers, okay, will summarize the distance to the destinations inside its own area and advertise to the other area border routers. Okay, so that's how the area border routers discover each other at the higher level. Okay, and those advertisements will be shared by also the backbone routers and the boundary router.